Let's talk about Chapter 7, the hazards of pressure, steam, and electricity. So pressure is defined as either the force exerted against an opposing fluid or the force distributed over a surface. It's written as pressure equals force over area. In customary units, we refer to this as pounds per square inch, so generally PSI. High pressure is defined as anything greater than atmospheric pressure. So what's atmospheric pressure? Atmospheric pressure is the pressure exerted on you and everything around you by the weight of the air above you. So if you took 1 square inch, so think maybe something the size of a quarter, and you look up, the air above that 1 square inch going up into space would weigh 14.7 pounds, and that would be exerted over 1 square inch. The atmospheric pressure typically is 14.7 psi. Now it's written differently for different units of measurement. In inches of mercury, it's written as 29.9. This is what you'll see when you look at a weather forecast, so the barometric pressure. So it's not always constant, it does change, but it doesn't change much. 14.7 psi is a good number for atmospheric pressure that's always present. So different industries define high pressure differently. So you walk into a plant, you see a pipe that says high pressure, and you got to work on it. You want to know how much pressure is in there. I mean, you're going to depressurize it to work on it, but you got to know what kind of pressures you're dealing with. So the American Gas Association says anything over 2 psi is considered high pressure. So it seems like this doesn't make sense, right? I just said that atmospheric pressure is 14.7 psi. The American Gas Association says anything over 2 psi is high pressure. It doesn't add up. The reason is that the numbers I'm quoting for the American Gas Association and the following that I'll mention are gauge pressures. So they take into account that 14.7 psi. The reason is that atmospheric pressure is just always there, so we don't include it in gauge pressure. So when you read the air pressure in your tires, it'll say 35 psi. It won't say whatever 35 plus 14.7 is, even though that's the true pressure in the tire. So we're talking gauge pressures. American Gas Association says anything over 2 psi is high pressure for that industry. The American Society of Mechanical Engineers says anything over 15 psi is considered high pressure. OSHA says anything over 900 psi is considered high pressure. So the military has their own system for this. Low pressure is anything from 14.7 to 500, and they go up to ultra high pressure, anything over 10,000 psi. So you have to think the military, they have aircraft carriers and tanks and high performance jets. They have all kinds of equipment that runs at very high pressure. So the point of all this is to say that just because you see a label that says high pressure doesn't mean anything in particular other than it's more than atmospheric pressure, and it should be depressurized before you work on it. So let's talk about some of the hazards of pressure. The first are leaks, next pulsation, vibration, release of pressure, and whiplash. And in the following, I'll talk about some of them in more detail. So the first and most obvious is the rupture of a pressure vessel. So when you see on the news that somebody's hot water heater shot through their roof and, put a big hole in it, this is a pressure vessel rupturing, which we do not want. It happens when the actual pressure inside of the vessel is greater than the maximum design pressure of the vessel. So these can be slow ruptures where you might hear a rivet pop or a weld crack and have time to get away, hopefully, or a fast rupture, in which there's going to be an explosion and the rupture is nearly instant. I'd like to add that in an industrial setting, you can't count on slow problems occurring. So if you're dealing with a crane and it's going to fail quickly. A lot of industrial things are heavy, they're made out of steel. If they do fail, they fail faster than a human can react. Unlike, say, a tree. If a tree is going to fall, you might hear a branch crack, you might see it slowly falling over, you could get out of the way. Industrial accidents typically happen very quickly, so you have to plan beforehand, so either you know what to do if there is an accident and there's mitigation, or you create a situation where the accident does not occur. So the next pressure hazard are boiler explosions. These occur if the steam output is blocked or restricted and causes an increase in temperature and pressure. Now, there's a couple ways to mitigate this. The first is what's called a fusible plug. So this melts. It's made out of a material that will melt when it's not covered in water. So as the water level drops and exposes the fusible plug, the steam will melt it and it will release the pressure in a somewhat safe way. The next is the pressure relief valve. So these open when a desired pressure is reached. Now, the simplest form is just a spring that has more spring force than there is pressure in the vessel to open it. So when the vessel reaches a certain pressure, it overpowers the spring and allows the steam to escape. When the pressure goes down, the spring overpowers the steam and it closes, or it should close. The next are dynamic pressure hazards. So there's a few different kinds of this. One of them is when a gauge breaks. So occasionally a gauge pressure will overpower a gauge and the face can explode and send particles into motion toward an operator. The next are air, oxygen, nitrogen bottles. They have a lot of pressure in them and they have a flimsy valve on top that is susceptible to breaking and turning the pressure vessel into a missile that can shoot through concrete walls. The next are whipping hoses. Air hoses are common in an industrial setting. If there's enough pressure in it, so say 120, 150 psi, and that hose is cut, say somebody drives a forklift over it and it cuts the hose, it can whip around and cause serious damage to people and equipment. You never want to try to grab a whipping hose. You want to go to the source and turn the air off so the hose stops moving by itself. The next dynamic pressure hazard is the water hammer. This is caused by the incompressible nature of water. What happens is if there's a blockage in the system, say a valve slams shut, the moving water stops. It's not compressible, so that energy is going to go backwards. This can cause a shock effect and result in an increase in pressure. This can rip pipes off of their mountings, it can rupture pipes, it can cause all kinds of damage. So the way to avoid it is to open and close valves very slowly if possible. So this is easy by hand, you just open and close the valve slowly, right? Where the problem comes in is when you have computers that are controlling valves, you have to make sure you program in their open and close times. It's something you don't want to miss. Water hammers can be very dangerous in high pressure, high volume systems. The next is vacuum. So vacuum is an interesting one. Vacuum is negative pressure. What can happen is a vessel that is designed for normal pressure, right, positive pressure, if exposed to vacuum, can crush. It can crumple under the vacuum. The reason is that pressure vessels are not designed to take vacuum. Just like a big oil tanker ship is designed to take the pressure of the water all around it. If you took one of those big ships and put it on dry land, it would fall apart, right? It's just a design issue. The same thing with pressure vessels. The main reason they could be exposed to vacuum is condensation, so a lot of tanks are cleaned with steam to get whatever's in there out. If you clean a vessel with steam and then close it so the steam can't escape, the steam will condense and reduce the pressure in the vessel, causing a vacuum situation. The next topic is the detection of pressure hazards. So when you're working on pressurized systems, you always want to depressurize it. If you're trying to find a leak, you never want to put your hands near a suspected leak, okay? So some of the ways you'll identify a leak are sounds. Sometimes you can hear it. Streamers, which are just bits of paper or even like a trash bag, will move if exposed to a leak, right? The next is soap and water. So if you have a leak in your automobile tire, you can just take dish detergent in a spray bottle mixed with water and spray it all over the place, and the place with the leak will have little bubbles coming up. This can also be used in an industrial setting. It's pretty clean and easy to do and cheap. The next is scent. Certain gases and chemicals have a scent added to them. So propane and natural gas both have scent added so that you can detect if there is a leak. And the last one are commercial leak detectors. There's all kinds of varieties for specialized tasks that have their own operating methods. So let's talk about the hazards of steam. In an industrial setting, steam is used all over the place. It can be used for power generation, heat for boilers, purging gas, or for snuffing out fires. Lots of different uses for steam, even heating. The thing with steam is that it occupies 1,600 times the space of water at 212 degrees at regular atmospheric pressure. This expansion of steam can cause big problems. Also, on the reverse side is where vacuum comes from. So steam expands and then it contracts as it condenses, right? So steam explosions result when steam or when water contacts something hot enough to turn the water into steam. So think if you're heat treating parts, if you have a little part that's red hot and you put it in a bucket of water, it's no problem, right? There's enough water there to take the heat, a little bit of steam puffs up, no big deal. Say you take a big part, it's red hot, you put it in a pan of water, right? All that water is going to flash to steam. Now you don't want to be near it, but it's not going to cause an explosion. If you take a big red hot part and put it in a closed container that has just a little bit of water in it, now you could have a problem because that water is going to flash into steam and it has nowhere to go. It's going to expand 1,600 times the water volume and it could cause rupture and explosion. Okay, so a steam explosion is what caused the big problems at the Chernobyl nuclear disaster. There's essentially a bunch of water under and in the reactor. It flashed to steam, blew the top off of the reactor, and threw radioactive contaminants into the atmosphere. Let's chat about the hazards of electricity. So these fall in two principal categories. The sparks and arcs can cause fires or explosions, and electrocutions can occur. So electrical shock injury, another term for electrocutions, depend on two factors: the amount of current and the current path. The amount of current delivered is determined by the voltage and the body resistance. So body resistance is essentially just how wet the part of your body that touches an electrical hazard is. The current path is the path the current takes through your body. So if you touch a live electrical wire with 2 fingers, it's going to go through here. If you touch a live electrical wire with one hand, then grab it with the other, it's got to go all the way through your body, okay? If it goes through your heart, you can have big problems. It only takes a few milliamps to stop your heart or cause enough issues to have serious health consequences. The body resistance is determined by how wet you are. So if you drop a blow dryer into a bathtub, it's a serious situation. Because your body resistance is 0, right? You're covered in water. A good way to think about this is a 9-volt battery. So if you take a 9-volt battery and touch both terminals at the same time, nothing will happen, right? If you lick a 9-volt battery, right, it hurts because of the body resistance. Your tongue is wet, your fingers are not. Your tongue has a low resistance, your hand has a high resistance because it's dry. The next category are sparks and arcs. These occur when electricity jumps through air. So we harness this when welding, right? We use an electrical arc to create heat to melt metal. But when it's in an electrical junction box or something, it's not a good thing. We don't want it to happen because it can start a fire or unleash an explosion. Another hazard are arc flashes. So when an arc happens, there's bright light. So think about welding. You do not want to look at a welding arc. If you open an electrical panel box and there's a lot of voltage and an arc happens, there could be enough light to blind you, either temporarily or permanently. And the arc can also cause an explosion called an arc blast, where, just like in welding, the arc can melt metal, vaporize it, and basically cause an explosion inside of an electrical panel. The next hazard is static electricity. So static electricity can build up and cause a spark or an arc. So friction causes static electricity, and static electricity can be developed through liquids. So when liquids move through pipes, there is static electricity being developed, just like a wool sweater over a rug, okay? So anything in movement has friction and will cause static electricity. Now, all processing plants have a way to deal with this through bonding and grounding. So bonding is when you connect 2 metal objects together, usually with some kind of copper, but any metal will do. Grounding is when you have a copper rod stuck into the ground connected to a metal object. This grounds it and gives the static electricity and stray electrical currents somewhere to go. So every house, every mobile home has a copper stake in the backyard somewhere to ground everything in the home. Large chemical processing facilities typically bond vessels together and have one or maybe several grounding rods. You typically don't ground every single metal object, like every building would have a grounding rod, then all the equipment would be ground or bonded together. So that's it for Chapter 7.